Well done, we made it. The last talk of the day. We finally have one of those elusive data scientists that we've been talking about. We had DevOps people, we had developers saying like, and the data scientist does that, the data scientist does that. So now we got someone who does it, and is even a doctor, Dr. Robert Hoffmann from Microsoft Austria as well. He's going to talk to us about practicing data science in the cloud. And he's got a Blinky thing with him, so I'm excited already. So let's see what we can see about that. Last talk of the day.
Thank you. Thank you. Glad to be here. Can't see much with the light, but I suppose you're all here and attentive. Great. So I will, in fact, talk about how the cloud is a really perfect environment for doing data science. But before I get into this, let me briefly tell you where I'm coming from. So I joined Microsoft 2 years ago. Before that, I was working in bioinformatics research for more than 10 years, working in Spain and in the United States for a long time. And I had the chance to work on big data topics from really all perspectives. That's the good thing about research, from data engineering to data analytics, a lot of software engineering. So I really saw all angles of it. And of course, being basic research, I was deep into Linux and into open source. And well, when I then finally joined Microsoft, I mean, you can imagine the shock that it was, right? Should shock, indeed. Wasn't that bad, because it turned out that the new Microsoft is actually cool with Linux. It's cool with open source. So I'm cool with Microsoft. And it turned out that the Azure cloud is really a unique playground for doing data science. So the data science process, probably you saw it a couple of times today. It's really we set up a goal, a business goal. I don't know, reducing the downtime of our machines, increasing customer satisfaction, recommending the next best movie, these kind of things. So we have to sort out our data, come up with an experiment, devise hypothesis maybe on our data, prepare the data, and finally try to implement a model, train a model on that data that gives us meaningful predictions. That's the data science process. At the end, of course, we evaluate and see how close we came to our initial goals. So it's a highly iterative process. And every time that you go through that process, through that cycle, of course, you learn. But you will adapt. You will change course. I don't know, you might even change your tools of frame set. You will change the way you transform data. Maybe you find a new data source. So really anything goes when you go through these cycles. And the environment that you would need for that is an environment that can cope with it and also maybe even speed up that process. Of course, if your data set is small and you're a one-man show and you're working on your notebook, you might even be able to achieve this flexibility, because you're a one-man show. But we don't create models just for their own sake. I mean, it's great when our models produce better and better predictions. But unless our predictions lead to influence our actions, they can be quite useless. And in the real world, we find for many reasons quite often that there's a gap between those people that do the modeling and those people that operate the models. And of course, sometimes even modeling is really more about prototyping, and then operations is re-implementing a model using another language, Java, or something like that. So there's usually a divide between these two parts, modeling and operation, and it's slow. And actually, as a data scientist, you should want to be part of that larger picture. I mean, you should want that if you come up with useful models, you would want them to be released quickly. deploy it immediately. I mean, if you come up with a model that reduces downtime for a machine, you want it to be used and immediately, I don't know, trigger alerts, improve the fate of the institution that you work for. So that's one thing also for the data scientist intellectually seen. It's very useful to be part of this larger feedback loop because your models get deployed, they get monitored, so you will receive new telemetry on your models, you will receive new data that again helps you in the modeling phase to improve on your models. So you can also benefit from that. And again, we'll need an environment that is able to integrate these two parts, allow you a very agile way to model, and on the other hand, enable the operation of your models. And then, of course, if we start to model on big data, the picture gets much more complex. You'll have to spend a lot of time in other things than modeling. Modeling is just a small part of that. It's well known that you then spend on configuration, on maintaining tools and machines, data preparation, data engineering, maintaining your serving infrastructure. All these things take up a lot of your time, and they make the picture more complex. And with this complexity, there comes dependencies on other people, on other processes. And with these dependencies, there comes waiting. And waiting is painful, as we all experience. Waiting is painful. It's waiting for getting access to a new data source, waiting for a cluster to be finally updated or set up in the first place. Tools that we need to be installed and prepared. So that's all annoying. And the worst for data scientists, really, in terms of waiting, is you have to wait. If you have to wait for a long time until your model computes, until it's trained, that's horrible. That's like when you're watching a movie or so, and you get interrupted. That's annoying. That's how annoying it is. And remember, we're in this iterative cycle of creative thinking, of exploring our data, of coming up with new hypotheses. So every time we have to wait before we can do the next step is actually distracting us and will certainly take momentum from us. So the cloud really improves on, I would say, all these aspects that I was mentioning before. Speed, for instance. If your model takes, 3 hours to compute, to train, why not get more machines, maybe with a GPU, and finish within minutes? Now, that's feasible in the cloud because you can take resources in the cloud only for that time that you need them. And so it wouldn't make much sense to maintain your own server for a database when you can get a managed database in the cloud, for instance. And this works because it's a sharing model. It's like car sharing. Yeah? So no person alone, no enterprise alone needs that much amount of compute power. I mean, look at it, it's absurd. Is one of our data centers, of the Azure data centers. Disclaimer, I'm from Microsoft, so I find those the most beautiful. I guess the other ones are not bad either. And these data centers, they are filled with containers that you can see here. And these containers filled with CPU power. Nobody gets into these containers. They're just connected to electricity, to power, maybe cooling, to networking, of course. Yeah. Nobody goes into them. And if a certain number of machines within these containers stop to work, the entire container gets replaced. And that was one data center. There are 50 regions around the world, more than 100 such data centers. And you can pick your region where you want your data to be settled and where your compute workloads will be located. And that's what I meant with being a fantastic playground for doing data science. And this sharing of resources, of compute resources, makes especially sense in machine learning, where we often face an imbalance between the computational cost of training models and then of making inference, predicting something with our models. So if we take deep learning, multi-layer, deep neural network to classify images, it could take depending on the hardware, of course, but it could take days to train on millions of images your model. Then on the other hand, to use this model, once trained, to predict a single image, this can be done in less than 2 milliseconds on, for instance, our FPGA hardware in the cloud. And this imbalance is actually it's very pronounced in deep learning, of course, but we find it in all machine learning scenarios. So let's take a connected factory scenario, for instance, where our machines produce sensor data, and we want to use these sensor data to predict downtime, failures, for predictive maintenance scenarios. Or use computer vision to inspect on the quality of the products that are produced. Now, in both scenarios, we would create huge amounts of data, sensor data and image data. And of course, we have to keep all that historic data because we don't know yet all the use cases of this data. So we have to keep it for one. And then we'll need, from time to time only, we need a lot of computational power to create models on this data. But then really for production during the rest of the year, we need only very little to make use of those models. So it's actually very difficult to imagine how you could manage such an imbalance on-premise in a cost-effective way and let alone in an agile way. So that's actually, as I said, a perfect scenario for the cloud. In the cloud, you have storage, which is secure, it's reliable, it's inexpensive. And the cloud is also a place where you can have your data scientists collaborate around that data, explore it, come up with ideas for models. You can also invite other collaborators from, I don't know, academia, for instance, to help your team. And then when you want to create a model and compute it and train it, you actually have the resources to do that, and you only pay the time that you use it. If it should be necessary, and in this scenario it makes a lot of sense, you can then deploy this model, once trained, to the edge, as we say, or on the production floor. Yeah, so where you can make inference on the products that are produced within milliseconds and without latency. So once the model is trained, you don't have to go back into the cloud for predictions. And of course, in this picture, if it turns out that your data science team would actually be more effective using another tool or a completely different framework in the cloud, you would have the agility to change. And the next time you go through the cycle, your team can do better. So I want to give here an example and a little demo on an example of a machine learning pipeline, going through all the steps, ingesting data from a data source. We'll collect it at the IoT hub. That's our endpoint in the cloud. Collect that data, store it in a data lake where it's cheap, inexpensive, secure, and then we'll take compute power for the computation of models. And then, as we saw before, for this continuous integration and delivery, we also use Azure Machine Learning Services to then put this model into operation, where we can monitor it and ideally connect it to our back-end business applications to, for instance, trigger alerts, invite the technicians to service our machines. So there are as many, let's start at the data source. There are as many data sources as there are use cases. I brought with me here a very, well, it's on the smaller side of data sources. But I don't know if you can see this, but it's working really hard. I think it will take about 100 years to produce, well, maybe not even then, big data. But we can think of it as our connected factory. And in fact, it is measuring sensor data, temperature, humidity, acceleration. And it is streaming that data to the IoT hub right now. So and what we are going to look at is to predict anomalies, outliers in the sensor data that is produced, similar to the connected factory scenario. So for detecting the outliers, the anomalies, we can choose from, we are not limited. As I said before, we are fine with open source. We can use TensorFlow and autoencoders to detect anomalies, or we can just use a one-class support vector machine to do that using scikit. It's not just our goal to predict the anomalies. We also want to make use of what we heard before, this continuous integration and delivery. Yeah, so that's our goal. And the Azure Machine Learning Services actually will help us to achieve that. So this service does a lot of things for us. For instance, it will instantiate compute targets for us, where we can do the compute. Different types, like it could be a GPU machine, or it could be an entire cluster that is instantiated. And then it will push out the machine learning training code out to this compute target, collect the results, and the final model that we trained. And that's the upper part, that's the training part, the left, the modeling circle, right? So we can go multiple rounds through this cycle until we're happy. But then once we found a model that is actually useful, we want to release it, package it with its specific version where we know and are trusting that it's our best attempt. And this model will then be packaged into a container, a Docker container. And this allows us to deploy the model as is, with all the dependencies and all it needs to work, deployed anywhere. So we could deploy it in another cloud. We could deploy it in Azure Container Services. We could even deploy it on the edge again at the connected factory. And that's actually what we're going to do. So the Azure Machine Learning Services, they are the back end. They do all this magic stuff for us. But we will control these machine learning services through a lightweight Python SDK that we can use from anywhere. So we just have to choose an environment where we can actually do that. And these are just 4. In the cloud, there are numerous ways to do that and to find yourself a workspace. But you could use that Python control from your local machine. You could use a data science VM that's a VM prepared for data science tasks. There are a lot of things installed. But really, the VM has the advantage that you can scale it vertically. You can choose a machine with a lot of CPU power, maybe GPU if you need it, lots of RAM. We could use Azure Notebooks, that's Jupyter Notebooks, as a service, basically. Or I want to mention Azure Databricks. Databricks is a company that, from the people that invented Spark. So it's very tightly integrated in the Azure environment, and it's basically a Spark environment where you can use clusters to do machine learning, and it's a great place for all kinds of workloads and for collaboration as well. For the demo, I'll just use the local machine, and for that I have to switch. That's good. So that's the Azure portal actually. So on this Raspberry Pi, there is the Azure IoT Edge runtime installed, and it has the advantage that it can serve for our machine learning models packaged as Docker containers. It serves as a runtime for them. So this runtime is installed on here. I created a module that picks up the sensor data and transfers it to the cloud, to the IoT hub. And once we're in the cloud, now I want to do two things. I want to stream that data onto the data lake, serialize it for our exploration then, and for then training a model on that data. And on the other hand, I want to send it to a dashboard that I can visualize this streaming sensor data in real time. And that's what you see here. I'm using something called Stream Analytics, and where I can define a quite simple SQL statement that will send the sensor data, for one thing, to the storage and also to the Power BI dashboard. So that's that. And here we'll have the dashboard coming in real time. So if I move the Pi, we'll see in real time the change in sensor data. It's a slight delay. It still has to travel into the cloud. We see different things that are collected here, like temperature and pressure and things like this. We are really interested in the acceleration information. So then, as I said before, I will control the machine learning services using Python. And that's what we see here. It's the Jupyter Notebooks. So if you don't know that, Jupyter Notebooks allows me to execute code, for instance, Python. And also, it keeps my results. It keeps them, and basically it allows me to keep track of my experiment in a notebook fashion, hence its name. So in the first line, I just get a quick sample of the data that we are uploading. So as I said, there's temperature and stuff like that. There's also the acceleration data in the different coordinates or dimensions. And so that's that. And on this data, we'll train a model. And that's Python. And really, you don't have to follow here all in the details. I want just to give you the idea of what we're doing here, and then also at what points we're using the machine learning service, and how easy it is actually to make use of all that. So that's the script. Here, that's the logic. That's where I put all my imagination to create a model. That's the part. And well, it looks very often very similar. We import some libraries. I even receive parameters. I point out this one parameter, NU. It specifies details about how my algorithm will run, but we'll see it later. That's why I mention it. We, of course, have to have access to our data. I derive a few. I do a little bit of mini feature engineering, basically combining the different dimensions of acceleration into one single vector. And then also I want to get past time steps from the acceleration data into together with my current data. And here's finally where the model is trained. So it's really one line. That's not the difficult part. The model is trained. I also do some prediction kind of on test data. And then here the model gets output. So that's the final result that I want to receive. It's a trained model serialized here as a pickle file. And one thing to point out, I'm accessing here, so this will be executed not on my local machine, but in the cloud and using the machine learning service. So in my script, the only thing I want from my service is its logging function. So what I log out here is the NU parameter and my test results. We'll see this again later, why this is useful. But that's the script. So that's it. Now we actually want to make it run. So I'm on my local machine, and I'll execute those steps that are necessary to use the machine learning services. So first of all, I have to get the library into memory. I have to connect my local notebook to the machine learning service, of course, because I want those two to interact. So I do this here. I also defined a compute target. In this case, I'm using a data science VM. As I mentioned before, it's a machine, it's a VM in the cloud that I'm using for this. But I also show here that you could use different targets. I mean, for this little mini demo with small amount of data, the VM is an overkill already. But if you have larger data, maybe a neural network that you have to train, you want a VM with a GPU. You want maybe distribute training of a model over multiple nodes, and you might want to use a batch AI cluster or Databricks, as I mentioned before. Okay. So I'll do this here. If I already have a VM in my created before, it will rediscover it, and this is it just did. Now create an experiment. That's basically a container for our activities. It's more an organizational feature. And here is the actual part where I'll push out the training to that compute target, to that remote machine, and define the parameters that I'll pass. So here this NU parameter is set to 0.4, and the communication with the Azure Machine Learning Services has started. And now what's happening behind the scenes is that this training script of mine, with all the dependencies needed, is packaged as a Docker container, built, transferred to the compute target, executed. Once there are results, these results are picked up and brought back into my Azure Machine Learning workspace. So that's actually quite a round trip that it does for me. And I'm only here on my notebook. So we saw that this completed quite quickly. I have here my parameter that I've set before, and because I logged it, and my result. And this you can actually, and that's the whole idea, as we said before. I might want to experiment with changing the parameters, changing the algorithm that I'm using. So now I'm using a different one and execute it again. In the Azure portal, I have my machine learning workspace where all these activities are reflected. So for instance, we see here my experiments. That's the one that I just created. And within that experiment, there are multiple runs that I did. A couple of them failed at the beginning. A couple of them I tried so that the demo works. I get information like how fast it is, but I can also add here information that is specific to my project. So here, for instance, I added a chart that plots my recall, my result, the efficiency of my model, if you wish, against this now famous NU parameter, right? So I plot these two. And so, I mean, it usually doesn't evolve necessarily to a better and better model. I mean, you'll try, you experiment, things will fail. But here you have a nice overview, and you can pick the model that is actually doing best, in which case, in this case, actually, it's using a small NU parameter. And when you then finally, you decided you found a model that works, you can destroy the compute target. You will not need it anymore. And then you can register your model. You can register it with a specific version that you basically now release to be deployed by your operating team in the spirit of continuous integration and deployment. So here, besides my experiments and the runs I did, I have also the compute targets that I was using. So in this case, it's our Linux VM. And I have these models that I registered with their version number. I just added a new one. And then I have also here the possibility to create images, Docker containers. So if you know about Docker containers, are essentially mini operating systems. They include all the libraries that you need to make your model run. So they are in that image. And then can now go to the IoT Hub, switch to my edge device, which is this one. And as I said, my edge device is running a runtime, so I can now add a module, a machine learning module. I have to tell it what Azure subscription I'm using. I have to tell it the workspace I'm using in. But then, give it a name. But then it will find the module that I just published. And going through the next and next steps, I would deploy that model right at the edge. So I'm closing the entire cycle. So I did this before. So now that I have that model here running locally, it can detect our anomalies, flash in red as it does here, excitingly, but it could also trigger an alert, invite a technician to maintain the machine to work efficiently. So I hope I could show you that it's actually pretty easy and straightforward to do machine learning very conveniently using different environments, different compute targets from end to end, from modeling to operation, and then even deploy that model. What I want to say as a final remarks is that we live in a world that is changing at an exponential speed. So that's Moore's law. You know that, how computational speed is increasing exponentially. But it happens everywhere where human activity is intense and technology is advancing. For example, in my field in bioinformatics, or sequencing the first human genome cost about $100 million 20 years ago, and it fell much faster than Moore's law, and now you can get the genome sequenced for just $1,000. So this is happening everywhere, and in this scenario, we very often speak of the Red Queen paradox. It's a world where we must run as fast as we can just to stay at the same place. And I hope I've shown you that with the cloud, you might be able to pick up that speed and concentrate on the things that are the cool stuff, actually. Thank you.
Excellent. Again, we have no question time because we have a hard pass here at 7 o'clock where we have to leave the room. Yes. I hope that was useful. I want to thank everybody here that you were actually good with the questions on Slido. You were good with not throwing things. That was nice. I wish you had a wonderful day. We have one last Slido question, which I don't know we're going to bring up anymore, but if it comes, I'm not going to be surprised. The question was like, what was the one thing that you would take away from here today, legally? And as it's one word, you can use a German word, which normally is a sentence, so you could explain a lot of things. If that doesn't happen anymore because we're over time, yeah, there we go. In one word, what are you taking away from today? You're not taking Microsoft away. We're not giving it away. I'm sorry. That's not going to happen. While this is happening and while we see these beautiful things that are coming, I want to thank the Slido people for making my job easier, for filtering all the naughties out and the stupid questions. There are no stupid questions, but some of them are just stupid to answer. And I hope that all of you will come to the after party at Horst at 8 o'clock, which apparently is a big thing here in Vienna. And hopefully we're going to have a great time there. And if not, I see you bright and bushy-tailed tomorrow morning. I will be bushy for sure, because the hair is like weird with the hotel shampoo. And I hope you've learned something today, and please come back tomorrow, and it was great being here. I have to say, at the WeAreDevelopers, the other event, people tweeted more and asked more questions on Slido, but that's not really any criticism that you should not take serious. So I have a great night at the Horst, and I might see you there, and if not, I see you tomorrow morning. It was great working with you. Thank you very much.